Welcome. So, this is the final equivalent circuit of the induction motor that we have derived, and it is I am now happy. I have applied voltage V bar m, current drawn is I bar m, experimentally I can determine, and it has got a meaning. No question of positive sequence, negative sequence, those things I have taken into account already. And then considering this, I am just telling you calculate this current whatever it is, and calculate this current whatever it will be after it is a circuit problem now, you know the value of this slip. Then the total torque will be this current square into R2 dash by 2s minus this current square into R2 dash by 2 into 2 minus s will be the total torque. It is no point in telling per phase equivalent circuit. This is the equivalent circuit of the machine. One phase after all is there, and it is for which machine? The machine which is running on a single coil, mind you, that auxiliary winding, this thing, it was some tricks I did to translate this two currents as balanced two phase current. It is not there at all. That is why I have assumed I bar A equal to 0. So, this is I bar M, this is I bar M, and this is V bar M. So, this is the equivalent circuit of a single phase induction motor on running on a single winding, running on a single winding, single main winding. Okay. And the expression, now I will just call this current as I 1, this current as I 2, so that I A pi B I defined something, 2 I F B it becomes, let us call this current I 1, this current I 2. Then I will say torque will be I 1 squared into R 2 dashed by 2 s minus I 2 square into R 2 dashed by 2 into 2 minus in synchronous watt, and the problem is solved. Sometimes it is interesting to note that this circuit is somewhat involved. So, how to solve this circuit? Some people do it like this, R1 X1 is there. What you do? This parallel combination you find out, equivalent, that will be ultimately between these 2 points there will be a resistance and reactance. Call this resistance to be Rf, call this resistance to be Xf, F for forward motor. Similarly, this impedance also can be written as Rb and Xb, and then this is the applied voltage V bar M, and this is the current I bar M. No, I bar M by 2. So, this is the thing. Now, what I am telling, the moment you do this, it is obvious that I 1 square into this one, I 1 square into R 2 dashed by 2 s, this will be nothing but equal to I m square into Rf, because they are equivalent. Similarly, this current square into R 2 dashed by 2 into 2 minus s is nothing but I m square into Rb. I mean, you can do like this or you can also do like this. This is the, as if the voltage applied across the forward motor, this is the voltage applied across the backward motor. So, this way also it can be done. I mean, if numerical problem is there with some slip, then better calculate this one, calculate this resistance. So, I m square Rf minus I m square same current Im square Rb, no I1, I2 now, they are same because copper loss will be same. So, this way sorry, these are divided by 2, important point. Okay. So, this is the thing, clear. So, this way torque can be calculated. Now, you notice one thing, suppose at starting condition A is equal to 1, if I put, I will just verbally tell, I will not draw any circuit. What the equivalent circuit tells me, is it correct? At least I can verify. A is equal to 1, if you do, then it will be R2 dashed by 2 here, this is X2 dashed by 2. If you put S equal to 1, this will be also R2 dashed by 2, this is the X2. Or let me draw, at S equal to 1, at starting, that is S equal to 1, equivalent circuit looks like R1 X1, and let me draw, visual impact is necessary. So, this is the thing, this will be R2 dashed by 2 only, this is X2 dashed by 2, and this will be also R2 dashed by 2, and this will be X2 dashed by 2, and these are of course Xm by 2, Xm by 2. Is not? This is the thing, this is Vm and this is I bar m. Do you think this current and this current will be different? No, this current, the way it divides, because these impedances are all same. Therefore, during this time torque will be this current, if I say I, this current will be also I, and I square into R2 dashed by 2 minus I square into R2 dashed by 2, that will be 0. Therefore, machine is unable to develop any torque at S equal to 1, which of course physically I knew earlier, but okay, equivalent circuit also tells me that. Now, the question is, what happens if sleep is other than 1? This is the equivalent circuit, na? Suppose you say sleep is 0.05, put some number, because range of variation of sleep value is 0 to 1, it is balanced two phase motor, from that S was derived, is not. Therefore, if you put S equal to 0.05, S equal to suppose 0.05, see only these impedances changes. What will be these impedances? It will be R2 dashed by 2 into 0.05. And what will be these impedances? R2 dashed divided by 2 into 1.95. These two impedances resistance values will be different. Therefore, at that time I1, I2 may not be same, and not only that, that is the expression of the torque. If you put better come straight here, S equal to other than 1, this difference will give you a result electromagnetic torque. Therefore, it looks like machine will develop some running torque. Is that clear? This is purely from mathematical point of view. So, it is correct, as the things were observed, the machine will be having running torque, but no starting torque is once again established here from the equivalent circuit. So, we now know what is what, and that is why at S equal to 1 machine will not start, Although there will be primary and secondary current, rotor bars will carry current, it will become hot, you must understand, like block rotor. But nonetheless motor will not run because the fields are aligned along the same line. But when the machine is running, that is why I told, if you give a twist, I mean try to help the rotor a bit by some external agency. If you in the clockwise direction you run, you will see even if you remove your that external agency, it will continue to accelerate on its own. Because at that time machine will have some sleep between 0 to 1, not equal to 1, and therefore, I now know from this equation, yes, it will develop a torque, and when that torque balances the load torque, it will continue to run at a constant speed over. Okay, after doing this, let us try to draw the torque slip characteristics of the motor. To draw the torque slip characteristics of the motor, we resort to this equivalent circuit first. After all, I now know this is a balanced two phase induction motor, is not? These two motors are at work, balanced two phase motor, balanced two phase motor. I mean go back to that primary thing, and it is a balanced two phase motor. Its torque slip characteristics will be same as that of a three phase induction motor. Similarly, this is another balanced two phase induction motor. Its torque slip characteristics, why it will be other than what we obtained for three phase induction motor, same. So, because each one of them is a balanced two phase induction motor in this case, therefore, torque slip characteristics of single phase induction motor will be like this. Suppose approximately this is S equal to 1, this is S equal to 2. Suppose for the forward motor, the torque slip characteristics will be just like that of a single phase induction, a three phase induction motor. And slip I have varied from 0 to 2. Why it is varied from 0 to 2, you will easily understand. Suppose this is the for forward motor, which is a two phase balanced induction motor. This is the torque slip characteristics. Suppose machine is running at some slip S. Forward motor is running at a slip S. What is a forward field? Forward field is the one which moves along the direction of the rotation. I define that way the forward field. And its slip value is Ns minus Nr by Ns. So, some number you get, say 0.05. Then what will be the slip of the backward motor? Backward motor slip is 2 minus S. If it is SF, this is 2 minus SF. So, forward motor torque slip characteristics is this. Suppose machine is operating at this forward slip SF, how much torque it has developed? This much. But there the story does not end. You cannot say that this is the net torque, because in my mind there is another field rotating in the opposite direction, and this sleep corresponding to that backward motor is 2 minus SF. For forward motor, if it is SF, it will be 2 minus SF. For example, if SF is 0.05, the backward motor, this is backward motor, this is forward motor, its sleep will be 1.95. Now, the question is, what is the torque of the backward motor? Oh, same curve I can use, only thing that value I have to read from here, 1.95. So, this is the backward motor torque, this is the forward motor torque, and then the net torque is Tf minus Tb, like that I have to do. If it is operating at this sleep, this torque, then whatever is the sleep, 2 minus s come this side, sleep is now greater than 1 for the backward motor, read this one, and the difference of these two will give you the torque. So, torque slip characteristics will be just like that of a 3-phase induction motor, and you now understand why it is necessary to draw the torque slip characteristics over a range 0 to 2, because I can then read the value of the torque from this curve due to forward field as well as due to backward field. For a given value of forward field SF, backward field it will be 2 minus SF. So, I will come here read this. So, this is how one can. If S equal to 1, suppose at starting, what is the torque developed by the machine, by the forward motor? This will be the torque developed by the forward motor. What will be the torque developed by the backward motor? 2 minus s, that is once again 1, same value, and the difference of these two is 0. Anyway, this one curve will do, but people nicely because reading this one, taking the difference, always you do. So, what you do, you draw this curve, take the mirror image and flip it. By that what I mean is this one. Are you getting? Instead of going there, reading this. So, if you drew like this, then at any slip, this is the forward torque, this is the backward torque. This is the forward torque, backward torque. Getting? This is a good idea. That is graphically, I mean, you reverse this, because for a given slip, you have to go there, 2 minus SF, read it. Instead of that, do a trick, that backward business, bring it here, and you have to take the difference of these two. So, this is Tf, this is Tb, this is also Tb, minus Tb, Tf minus Tb. So, what you now do is this, go to any value of slip, this minus this, you will get a point here. This minus this, you will get a point there. So, the resultant torque slip characteristics then will be somewhat, I mean, I am sorry, it will start from this negative value, it will go there, it will go there, Tf minus Tb, if you go on doing, it will be like this. This is the resultant Tf minus Tb. That is the torque slip characteristics of single phase induction motor running on single winding, running on single winding, running on single winding. And it is now clear to me. starting torque is 0. So, this torque slip characteristics of single phase induction motor must pass through S equal to 1 point, okay, and this will be there. Then the point of operating point will be decided by the interaction of the torque slip characteristics of this single phase induction motor with the load torque. Those things are known and it will be there. Therefore, this is the full torque slip characteristics of the induction motor, okay, running on single winding, that is very important. This is the starting torque 0. Therefore, it looks like a single phase induction motor has got a running torque, but no starting torque. It is not a good practice. I mean, there is a motor, you say somebody switch on the supply and ask somebody to rotate it, giving a rotation by hand, not a technical solution. Starting torque must be somehow developed in such motors if one wants to use it for practical purposes. That is, I will give the supply, motor will automatically run. But the problem is there is only a single phase supply and your motor has got a single winding. Whatever field will be produced will be a pulsating standing wave, which is broken up into a forward and backward field and things like that. So, starting torque, however, will be absent. Okay. I will come to this starting problem and we must do something to the machine now, so that starting torque is incorporated. Before that, just I have really done in this way. I brought some auxiliary winding mentally, I mean nothing like physically that auxiliary winding is not present, only main winding was there. That is what a single phase induction motor I will be looking for. Okay, there is a single winding only. Auxiliary winding was my thought process told, okay, assume some auxiliary winding, assume that current to be 0, then it is equivalent to a machine which is got a single main winding excited from a single phase source. Now, you can easily see that there will be, as I told you, two rotating field. Okay. One will be rotating in the forward direction, one will be rotating in the backward direction. Now, what will be the strength of the field? I mean, the question comes like this. Suppose this machine only I am considering, this is the rotor, this a point to be noted what I am telling, single winding, that is all. Here is V bar M, and I now know and also explained that if you excite this at starting no torque, machine will never start up, but if it is already rotating NR, it will continue to run. That is what the conclusion was. Now, the question is that while explaining that, I mean physical consideration I am telling, mathematics is fine, we have satisfied ourselves, but somehow still it looks like during a running condition it is also connected to a single phase source and it is also carrying a single phase current. What was the explanation that the motor will not have starting torque? Because this single phase current will produce a single phase MMF, pulsating standing MMF. For example, what will be the expression of this one? I will quickly do it. Suppose the MMF will be some M max, it could be B max also, it could be B max, but M max MMF into cos omega t, suppose, into cos theta. You recall? At a distance some theta angle you get these values. This can be just broken up by 2 and then 2 cos, it is the pulsating field. Please look at that lecture, pulsating field, standing pulsating wave. That is, the MMF distribution will be like this. You recall? No rotating business. But if you just manipulate it mathematically, divide by 2 and multiply by 2, you can write it as theta minus omega t plus cosine theta plus omega t, is not? So, here also I find, what is individual terms? This term cosine theta minus omega t is a rotating magnetic field individually, and cosine theta plus omega t is another rotating magnetic field, but rotating in the opposite direction. Therefore, a single phase winding carrying a sinusoidal current will produce a standing pulsating wave, but I now know that standing pulsating waveform can be thought of as 2 rotating fields of equal strength moving in the opposite direction. So, that is fine. Now, the question is, okay, if that be the case, during running conditions still this fellow is carrying a rotating magnetic field, sinusoidal current. It will also then produce 2 rotating field of equal strength moving in the opposite direction. Then why it should produce torque? Okay, torque will be produced somehow, we have seen, very concrete evidence we have got, but here lies the problem. Now, what really happens is, if the machine is rotating, there will be 2 rotating fields, no doubt, in the opposite direction, but the strength of the fields will be different. That is, at starting what will happen, 2 rotating fields, one is say MF, another is MB, both rotating in the opposite direction. With equal same speed, supply frequency decides the speed. But what I am trying to tell, when the machine is running with some slip or some NR, the forward field strength will be greater than the backward field strength. They will move in the opposite direction. Why? The answer is not far to seek. Strength of the field is decided by magnetizing current Xm. What is the voltage applied to this forward motor? What is the voltage applied to the backward motor? For a given value of slip, these 2 voltages, when the machine is running at some slip other than 1, these 2 voltage drops will be different. So, magnetizing current of this machine and that machine will be different. It is the magnetizing current that causes that strength of the field. Therefore, at starting, of course, the voltage between these 2 points are same, magnetizing currents are same in the forward and backward motor, and therefore, field strengths will be same. More on this after some time. Thank you.